Okay, hi everybody and welcome. Let me get my view correct. Here we go. Only 11 people. Well, so today we are starting to study a new culture. So the first days, the first 4 lessons were all about Babylonians. Right around the same period of time, you had society flourishing in Egypt. So we're talking about 1600 BC, and they developed math sort of independently of the Babylonians. And the Babylonian math, some of that stuff is still there's relics of it today, like the base 60 system for time, 60 minutes in an hour, 60 seconds in a minute. Babylonian square root algorithm is related to something called Newton's method, which is now sort of calculus way of finding square roots and cube roots and things like that. The Egyptian math is going to be very unfamiliar. It's not that it's harder. It's just it's like a completely different world, and it's hard sometimes to switch cultures after 4 days, because what happens when I'm studying this stuff, I really try to get my head into their culture, into at least the way they thought about the math. So I try to think about when I'm doing Babylonian math, I try to think, in base 60, and just get my mind around how they would have been thinking about this stuff. So then when I switch over to Egyptians, it's a totally different type of logic. And again, it's not harder. None of the days of the course are any harder than what we did yesterday. It's every day we'll start with something easy and build up till it's harder than it was, and then we start a new thing on the next day. So I mean, I guess obviously some days could be harder than other days, but in general, yesterday and the day before, that's the goal for this class, is about that difficulty level. So again, Egyptian math. So we have their numerals again, just to show you. They had symbols for one. Oh, sorry, I did not share my screen. Okay, so you can see here, and hold on. So they had a little bit of like a base 10 system thing going on, where they had a symbol for 1 and a different symbol for 10 and a different symbol for 100, a different symbol for 1,000 and 10,000 and 100,000 and a million. And then they would just sort of like Roman numerals, sort of stack them up. So you can see over here, 276 has 2 of their 100 symbols, and 7 of those horseshoe shaped things, 7 of those for 70. And then 6, they have, I see they have them in sort of groups of 3. Anyway, that was their system. So it's a little like Roman numerals. It's kind of a base 10 thing, but no, it's not base 10, because in base 10, all you need are the 10 numerals, 0 through 9.
Can I ask how they understand?
Say that again?
How do they understand the concept of like 10 or 100 if they don't have a 0?
So, so the concept of 10, just from way before the Babylonians and the Egyptians, they would presumably realize that, when they count and fill up all their fingers, they need some kind of way of marking a thing that counts as 10 things. So when they think of 276, they picture 2 big groups of 100 and 7 groups. So they don't need like a number 0. For instance, if they have 206, they have 2 of the 100 things and 6 of the 1 things. They don't need the idea that, oh, there's no 10s. So they don't need a 0. And since they use different symbols, unlike the Babylonians, where the 10s to the 60s place use the same symbols as the 10s place, there's no ambiguity. So they don't need a 0 to mark, oh, there's nothing in the 10s place. Because instead, they're using these, these symbols. I'll come over here. They have like the spiral, the horseshoe, and the 1. So when they see, 100 or, 206 or 200, they don't need a 0, because nowadays we need to say 206 to make it really clear, because it would be ambiguous if you didn't have the 0 there. Is this 2 representing the hundreds? But these 2 symbols stand for hundreds, so there's no ambiguity. In fact, you could even put, they didn't, but you could. It wouldn't be like crazy to go like that, and it's still the same idea. 200. There's 2 of these 100 markers and 6 of the little ones. So no, they do not need a 0. You only need a 0 if you're using the same type of numbers to represent the different places. So you can know, this number 2, does it represent 2? Does it represent 20? Does it represent 200? We wouldn't know if we have a positional number system with no 0 in it, but with these hieroglyphic type things, no ambiguity and no need of the 0. Now, most of what we know about Egyptian math comes from one of the more famous mathematical artifacts, which is called the Rhine Papyrus. And we know a little bit about the Rhine Papyrus because the scribe who made the copy of it was Ahmes. So sometimes called this, like the Ames scroll. Rhines, that's just a person. Henry Rhines in the 1800s purchased this thing, and it currently resides in the British Museum. And it's actually on display. Unlike Plimpton 322, which is hidden away somewhere in Columbia University. The Rhine Papyrus is a collection. Oh, you went to the British Museum, Tina? Did you see the Rhine Papyrus by chance?
Probably did. I'll look at my photos to see if I have a picture of it. I have so many photos from their Egyptian section. Is so huge.
Oh, great. Well, if you could find a picture of that and send it, I'll display it for the class. That would be very cool. I'd like to go see the Rhine Papyrus. I was in London 3 years ago, but I forgot that it was even there. I didn't even know it was there until just today when I was looking it up. So I missed my chance to see the Rhine Papyrus. The Rhine Papyrus is a collection of 85 math problems. And it has like an introduction that is like so the Rhine Papyrus has a reference table in the beginning, followed by 85 sort of problems with their solutions. And these problems range from basic arithmetic, multiplying and dividing, to algebra, algebra equations, like, x plus x over 7 equals something, like they become linear equations. You don't see quadratic equations in with the Egyptians. And then they have like proportional questions that are applications of their multiplying and dividing, where they're trying to figure out if you want to trade this much beer for this much bread, and what would be the proper amount of trading. The beer, they had like a measurement for how strong the beer was. So a really strong beer is worth more bread. And then they have geometry questions, things about area of a circle and area of various shapes and volume of various shapes. So a lot of people say that the Egyptians invented geometry. They needed to, because the Nile River would overflow and it would wash away all their boundaries of their markings that told where one person's oh, live transcription. Well, I have no problem with that. Let's see what happens.
Professor,
Live
was this a
transcription.
homework assignment like the Babylonian document?
No, this one's more of a textbook.
Okay.
Yeah, this one is written. It's very, very thorough. Actually, I have a translation of it that I'll upload. Like a full translation, and it is like almost like a modern math book. It's very, very clear. Each question is written, with explanations and like showing the work and some explanations about how they did their work. So there's not like a lot of mystery in this one because it's explained so well.
Gotcha. Thanks.
Are there any design
Sure.
documents from the pyramids showing the math used in the correct construction of the pyramids?
Oh, I don't know about their architecture and the math. I don't know of any documents. These questions are not like practical in that sense. I mean, they do talk about like a triangle and something that's a bit like the slope of the sort of how steep is the. It's not. They have a measurement they call the second, which is kind of like the slope of the side. And I could see how in pyramids you want to, you have to decide how steep is my slant height, going to be. But these questions are very sort of textbook type questions where people are trading beer and people are solving for unknown variables. It's actually pretty amazing when you see these questions. We're only going to do a small portion of them. Now, okay, so let's get into this. Now, I made and even if you're not able to access this, but if you are, this Desmos code has a spot for us to sort of go through. Every question we're going to do today is on this. So there's 24 like questions, and you could type answers in as you go along. But you could also type you could also just, if you're taking notes sort of old school way, because that's how I'm going to be doing it on the screen, writing the answers, but there's going to be spots to do this. So first I'm going to show you how the Egyptians multiplied. So the first question is 23 times 21. Now, one thing that's funny about their multiplication is that 23 times 21 is subtly different in their mind than 21 times 23.
Professor, can we get the code, please? Can you go back to the
Code, yes.
screen with the code? Thank you.
Yes, C6A ERG. The link's always student.desmos.com. Yeah, I also put one into the Google Classroom. C6A ERG. That's the code, but it's always students.desmos.com. Okay. So today I'm teaching you how to multiply and divide. Those are the two skills for today, but it gets really it gets pretty confusing, actually. You'll see, because especially when fractions are involved. So I'll show you when they think of 20. I'll show you how to do it. So to do 23 times 21, we're going to make a little 2-column chart. And the first row is going to be 1 and the number 23, which is the number that's on the left ends up being the number We always put a 1 here as the first column. You'll see where this is. The first column starts with the first row, first column is 1. The first row, second column is the 23. When they think of 23 times 21, they're thinking like 21 23s, kind of like what's 23 plus 23 plus 23. 21 of these versus 21 times 23, they think of that as 21 plus 21 plus 21, and there's 23 of them. Of course, we know you get the same answer, but it's just like a subtly different way of thinking about it. Now, the thing that so the Babylonians were really good at knowing that x plus y squared minus x minus y squared was 4xy. That was like their specialty. The Egyptians' specialty was the ability to double numbers and to take half of numbers and to know what 1.5 times a number was and to know what 2/3 of a number was. Those were their 4 skills. They were really good at doubling, halving, multiplying by 1.5, and multiplying by 2/3. With those 4 fundamentals, they did a lot. So much that some of these problems on the Rhine Papyrus take like an hour to when I teach them, it takes like an hour to go through just one of the 85 questions because they're so sophisticated with these things. But let me tell you how this works now. So you write 1 and you write 23. Now you double both of the numbers. So 1 becomes 2 and 23 becomes 46. Now, I said they're good at doubling. You double them again. Double 2 becomes 4. 46 doubling is 92. How they doubled them? It's tough to say. They just were good at it. I mean, I would guess they did 40 plus 40 is 80 and 6 plus 6 is 12. But whatever it is, they're really good at doubling.
I don't
And
understand. Why
again,
couldn't they just add another 23 to the 46 to get the triple?
well, they're not going to need it. Let's see
Oh.
what they do with these numbers.
Oh,
So now double again. And one last, we double to, I'll tell you how you know when to stop doubling. You stop doubling when if you were to double to become 32, oh wait. If you were to double this, it would become 32, which would already be bigger than the number I'm multiplying by, the 21. So we stop doubling when this becomes 16. It's less still than the number I'm multiplying by. Now, there's a funny, this Egyptian math is almost like an art, there's a lot of like creativity that happens in it. Unlike the Babylonian, which was very, very formulaic, multiply everything through by A, take half of this, square it, add it to this. This Egyptian math, there's like some like creativity involved in it. Because now what you have to do, we have these numbers 1, 2, 4, 8, and 16. We have to find the collection, which of these numbers add up to 21, which in this case, then we put a check next to 16 and 4 and 1. So 16 plus 4 plus 1 equals 21. So you have to find the collection of these powers of 2 that add up to 21. And you can always do this.
Professor, I have a
Binary.
question.
Yeah.
If we have more than one option that we can collect together, should be 21, what we can do?
There's only going to be one way to do it because you can only use each number one time.
Okay, thank you.
So you can't say I'm going to use 8, 8, 4, 1. You can only use one of each of these. And kind of like binary numbers, there's only one unique way to represent it. And while we're at it, if you're looking for, is there some sort of way to get it? a sneaky trick is you take the number 21 and you find the largest number that's less than 21, and then you subtract it, and then you check off 16. Then you say, what's the biggest number that's less than 5, which is 4, and you subtract that, you check it off, and then you're down to 1. Well, of course, that's 1. So that's a way you could find the collection of numbers that adds up to 21.
Okay, thank you so much.
Now you finish up their process by taking the numbers, the rows that you checked, so that the thing in the first column would add up to 21. There were 3 numbers on the right, and you would add together those 3 numbers, which evidently they were pretty good at just adding. We don't really know like what their adding algorithms were. I would guess it's kind of like what we do today. You collect, if you get 10, they would know that 10 of their 1 symbols can be replaced with the 10 symbol, and 10 of their 10 symbols can be replaced with 100 symbol. But we're not going to use their symbols. We're just going to add, old school, and get 483, which is the answer to the question. Now, the reason this works is because of the distributive property. 23, let me erase this over here. 23 times 21 is the same thing as 23 times 16 plus 4 plus 1. And then if you distribute the 23 through, it's 23 times 16 plus 23 times 4 plus 23 times 1. So that's works, why it works. You don't really have to know why it works for like the homework and for the final. I would just say, how would the Egyptians multiply 23 times 21?
Would you teach anybody to multiply this way?
No, there is something called the Russian peasants multiplication algorithm, which is very similar to this. And I have taught it as its own, not as a way that someone should multiply, but just as a curiosity, like trying to analyze why it works, that sort of thing. Now,
Mr. Professor,
Yes.
in now they're teaching number talks in elementary school and middle school, and a lot of it is halving and doubling. So Grant, that could be a good way. So number talks, you're doing mental math strategies, and the kids just kind of come up with it, and you don't even teach them really. You're just listing their answers and whether they agree, and you have a discussion about it. But one of the strategies is halving and doubling.
So that is pretty interesting. I've seen that with like when kids are learning their multiplication tables nowadays, like they're good at doubling and halving. So like if they know if they know, like they want to know what's 5 plus 6, they do double 5 and add 1. So doubling is quite an important skill, and it is kind of funny to see it coming back as a thing. The Egyptians knew that was like a really important thing, to be able to double things and halve things, and it's really good for your number sense also. Thank you for that observation and that extra how to relate it to what we're doing nowadays with math education. So what I would like you to do now is, can you do the same question but mix it, but switch it around? Do it as 21 times 23, just to verify that it gets the same answer. That is actually, and over here, my thought was that you would go like this: 23, if you want to type it into this thing. It might be easier for you to be, writing it, but it's fine. This was just my thought. If you're typing it in, you go like this. And then my thought was that over here in use or not, I would put like some kind of symbol, like an asterisk or something. That came out like a really small asterisk. Why don't we just put a number 1 there? 1, yes, I'm using it. 1, yes, I'm using it. This was my thought for this thing. And over here in the answer, you could write 21 equals 16 plus 4 plus 1. And then over here, 483. That was my thought for this. Okay, would you please now go over to page 2, or just on your paper, do the same question, but do it as 21 times 23 instead. So take a minute on that.
What's the code again? I'm sorry.
Oh, the code was C6A, is in the chat, C6A ERG. It's also in the Google Classroom. Okay, I'm going to take a quick look. If you've logged into the Desmos, but you haven't typed anything into any of the things yet, I might send you a little message right now just to like ask. Okay, looks good. So here I have the solution. And as you can see, it gets you the same answer. So on the final, you like, if it was a 8-point question, I'd probably take off a point or two if you accidentally, if you did it the other way. So it's just like a thing to kind of remember that when they did 20, whatever's on the left, that one is going to go over here. Okay, so that's multiplying. Now I want to show you.
Hey, wait. Don't move
how,
on it. Can you go back? I'm
what's
trying
that?
to copy some stuff. Just
Yes.
give me 60 seconds. Thank you.
Sure. Now today, the whole lesson is multiplication and division.
Professor, before you
And it
switch
feels
gears,
like-
Professor, I have a question. So they
Yep.
didn't understand the commutative property in a sense?
Well, they definitely would know that these two things got the same answer,
Okay,
but they would do it in different ways depending on nowadays, we would just set it up either way. We wouldn't even think that it makes any difference, but they definitely would have known that the answer becomes the same, but you always see them doing it in this way, being careful about which thing is getting multiplied and which one is like the thing that's like how many of those things there are.
right. So it's more like a
Now-
mechanics issue than a concept issue for them.
Yes.
Okay.
Now, if multiplying is done after 2 slides, why are there 24 slides here? Well, now we're into dividing. Now division, and I'm going to write down this question. Here's like the instructive example for division. Now we already know these are the same numbers from before, 483 divided by 23. So I'm going to come over here and show you their division algorithm. Now their division algorithm also has a 2-column chart, and it starts with 1. And then whatever the thing you're dividing by, that goes here. And we continue our chart by doubling, 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 doubling. And we stop when, if we were to double this number in the second column, if it would have gotten bigger than the thing we're dividing, the thing that we're dividing, we're not going to go to 32 because then we're going to have way over 483. So we stop here. And now we have to look for, get this, see these 5 numbers. We need to find a collection of those that add up to 483. Now that seems pretty hard. Like when we were trying to find numbers, powers of 2 that add up to 20 is pretty easy. Finding numbers that add up to 483 seems hard, except there's a trick to it. 483, you take it and you subtract the biggest number that you see on that list. And then you check off that one. And then you subtract. And then you have 115. We skip over 184. 92 is the next number that we can use. So we are going to use it. And then subtract. And then look for the number that's less than or equal to 23, and it's 23. So to get 483, we add together 1, 4, and 16. So I'll write down 1 plus 4 plus 16 equals 21. Now, that's the division algorithm. So why aren't we just done with the whole lesson? Anyone want to speculate?
Because there are other elements of division and multiplication, like fractions and decimals.
Yes, that's right. We might want, yeah, multiplying fractions and decimals. That's right. But even if I'm dealing with questions that don't have fractions and decimals in them, like this, like this question here, what complication might we run into?
Something that doesn't divide evenly.
That's right. If that 483 were instead a 485, well, unfortunately, they didn't just say remainder 2. They did something much more sophisticated than whole number remainders. So otherwise, their math would be a lot easier if down here, if this wasn't a 0 and they could just say remainder, whatever. But no, they are going to have fractional remainders. And it gets pretty hairy. So it's too bad because we seem to be flying through this lesson so nicely. Multiplication, done. Division, done. But no. Do I have for you? There you go. Just to practice division. Because on the final, this would be a perfectly good final exam question. Dividing 602 divided by 14. So why don't you take a minute just to do just another division practice. You can use a calculator for the subtraction. And for the doubling. just not for the dividing.
Professor, I think we need more rows on our table, right?
Oh, sorry about that. I see that now. So you can just, that's a good point. You could use that last row and then put the answer up in one of the use or not places. Thanks for pointing that out.
Yeah.
Unfortunately, it's hard to, once you publish these Desmos activities, you have to reassign them. It doesn't just update it for everybody. So you have to sort of create a new assignment and reassign it. So okay, let me see how people are done with that. Yeah.
Professor, I have a question.
Yes.
Okay, so the divisor is 14.
Yes.
Therefore, we're gonna stop at 8. So 1, 2, 4, 8.
Well, the thing is, 14 doubled. 14 times 8 is 112. So we're far from 602. We have to keep doubling until we get really close to 602. So the way you decide, I'll put up the answer. The way you decide when to stop is when, see, 112 would be too soon to stop.
Don't put up the answer.
We stop when we're trying to get to 602.
We're getting requests not to go over the answer yet. I guess people want more time.
Oh, okay. So let me
Sorry.
go like this then. Yeah. Yeah, these are a bit tedious. Now you can use a calculator for your subtraction and for your doubling. But yeah, take your time on this. Okay, let's take a quick look to see. Mhm. Okay, I'm going to put it up now. So as you can see, 602 minus 448, so I use the 32. I have a remainder of 154, so I subtract 112, which means I'm using the 8. Then I'm subtracting, I have 42 left. I subtract 28, I use the 2. Finally, 14. So it did go in evenly. Yes, the goal is to get as close to 602 without going over. So that's why we kept going to 448. Because only that's as close as I could get to 602. Yes, and it works. Yeah, I never even mentioned, why does this work? I think of it as working as the conclusion is that 43, or I'm going to say 14 times 43. But I guess that idea of thinking of it as subtraction, since we're subtracting when we do this, it kind of reminds me of that way also. Like I took away 32 14s, and then I took away 8 14s, and then I took away. So what's funny is this here is actually instructive about why it works, as opposed to in the multiplying question. Oh, we didn't have that in the multiplying question.
It's the
Well,
same
yes,
thing in
we did have it.
multiplication, though. It's just repeated addition. So that's why that works.
But in the multiplication, we did do a process where we subtracted away to maybe figure out which numbers added up to 21. Like, we were like 21 minus 16 is 5, minus 4 is 1, minus 1. But yes, this does work because division is repeated subtraction. So now we've done multiplication and we've done division, and we're 40 minutes into the class. Yet we have 2 more hours, because this is going to start to get pretty hairy, actually. I like have to take a deep breath before I start the next thing.
Good God, what's coming?
You'll see. So what if there's a remainder? I'll get the motivation first. What if there is a remainder? So what if I was doing 15 divided by 4? Let's just see how we run into a complication. So 15 divided by 4, I put 1 and I put 4 here. And then if I double it, it becomes 2, 8. Now, if I double it again, I'm at 16, which is already too big. But 8 plus 4 is 12, which is too small. So the thing you can do now is go back to the beginning, but instead of doubling, you can take half. And they had fractions. So half of 1 is 1/2, and half of 4 is 2. I'm going to make a note. We have 12, so we need 3 more. So by having the 1 and 4, instead of doubling the 1 and 4, I now have the number 2 there. And then if I have again, they do know they have fractions, but all their fractions are so-called unit fractions. A unit fraction is like 1 over a whole number. And they actually would write it as like a 2 with like a line above it. They didn't have like a numerator. They didn't need a numerator. That 2 with line over it meant 1/2, and a 3 with a line over it meant 1/3. We're going to write just we're going to write 1/2. We're not going to put a 2 with a line over it. We're going to write the fraction.
Hey,
and then when you
Professor.
have a fraction, yes.
Yeah, but if they're doing the half of 1, how do they get like odd numbers as fractions though? Like you're going from 1/2 to 1/4 to 1/8 to 1/16. There's
Great question. Yes, I'm glad you asked that question. Stay tuned for that.
okay.
That is an excellent question. So I have 1/4 though. I'm going to go. So having a fraction is the same thing as doubling the denominator. But as I mentioned, they're really good at having integers. So this 2 becomes a 1. And check it out. We now have a collection of numbers that adds up to 15. 8 plus 4. Actually, we need all of them. Oops. We always put the checks on the left-hand side just to. The Egyptians literally did this with the little check mark stuff. So 15 was 1 plus 2, which is 3. Now here's something kind of weird. They don't add 1/2 plus 1/4 to become 3/4 like we do nowadays. Their fractions are all unit fractions. They don't have a way to represent 3/4. So that's okay. What they do is they actually write what we call 3 3/4 as 3 with a half next to it, and then a 1/4 next to that. So that notation, 3 1/2 3/4, really means 3 plus 1/2 plus 1/4, which by our modern ways is 3 3/4.
Is it because they don't have an algorithm for adding fractions?
Well, they don't need to add the fractions because that 1/2 1/4 is how they represent 3/4 in their minds also. So they don't need an algorithm to add them. Just like, we look at the number 24 with a 2 and a 4. No one would say, oh, we don't know how to add 20 plus 4.
Okay.
We would just say, okay, that's how. So 3, we'll read this as 3 1/2 1/4, but know that that means 3 plus 1/2 plus 1/4. So it is kind of funny. We look at it that, from our modern point of view and say, wow, it's too bad they didn't know how to add, 1/2 and 1/4. But that symbol, 1/2 1/4, was just how they envisioned 3/4 anyway. Okay, so now let's look at the next question. Oh no, we don't have a next question. We have a next question, but not yet. Okay, here comes some history now. Egyptian fractions, 1/2, 1/3, 1/4, 1/5, they actually had a symbol for 2/3. They didn't have a symbol for 3/4, but they had a symbol for 2/3. So they have all the unit fractions and they have 2/3. So we will be allowed to use 2/3 also. 3/4 they would write as 1/2 1/4. This idea of representing fractions that we nowadays would put a numerator on top as a unit fraction, as a combination of unit fractions. So 3/5, I'll put it over here. 3/5, they would not write it as 1/5, 1/5, 1/5. You would think, why not? Pretty reasonable. Instead, they would find a sum of unit fractions that adds up to 3/5 where they're all unique. So for instance, 1/2 1/10 is 5/10 plus 1/10 is 6/10. So that's one way of representing 3/5. But what's funny about these unit fraction decompositions is that they are actually not unique. It's also 1/3 plus 1/5 plus 1/15. Oh, don't put the plus sign. You can't. You could put the plus sign. It wouldn't be that bad. But 1/3 plus 1/5 plus 1/15. Add those up. You get 5/15 plus 3/15 plus 1/15 is 9/15, which is also 3/5. So that's interesting. Unit fraction, let's call it decomposition. May not be unique. Now, the Egyptians were so comfortable with their fractions that if there were two different ways to represent the same fraction, like 3/5, they would be very aware that if you ever somehow were doing a calculation and somehow 1/3, 1/5, and 1/15 popped up, they would replace it sometimes with the equivalent representation. Now we will not get good enough at these to like be able to do that. But I just want you to know that they knew stuff like, oh, 1/2, 1/10. You see them in their math just encountering something like this, and just on the next step, they wrote this because they just knew, because that was just something they were familiar with. Here are a couple of more like curiosities. They knew that 1/2, 1/3, 1/6 added up to 1. Here's another multiple ways. 5/6 could be written as 1/2 plus 1/3, but could also be written as 2/3 plus 1/6. Remember, they had a 2/3 symbol. So often they would just, replace if a 1/2, 1/3 pops up, and if it was convenient for them for whatever was happening next in their calculation to replace 1/2, 1/3 with 2/3, 1/6, they would.
Hey, Professor, why did they just create a symbol for 2/3? Why not keep going? Why did they just find 2/3 unique?
Well, we're going to see what they do with these fractions in a minute.
Okay.
Keep in mind, they're very good at doubling and halving. They're also very good at multiplying by 1.5 and dividing by 1.5, which is the same thing as multiplying by 2/3. So doubling and halving and multiplying by 3/2 and multiplying by 2/3, dividing by 3/2, those are their operations that they like to do so much. So they would want to have a 2/3 symbol for that. But it's a good question. Why not keep going?
Right.
So as part of answering that question, let me tell you why it might be good to represent 3/5 as 1/2, 1/10. Like why in real life that might be useful. So 3/5 is represented as 1/2, 1/10. Let's see why. There is a collection of problems in the Rhine Papyrus where they're dividing, they're calculating out 1 divided by 10, 2 divided by 10, 3 divided by 10, up to 9 divided by 10, like getting fractional representations of those things. And they would usually say, we want to, hold on a second. Yes, they would say, like for 6 divided by 10, the question was, divide 6 loaves of bread among 10 men. That's what they said. They didn't say 10 people, but of course, women can get pieces of bread nowadays. So 6 divided by 10, and they would write the answer as 1/2, 1/10. They didn't have 3/5. Let's see why that might be good. Check out page 7. Here are the 6 loaves of bread, the rectangles. And if by modern way, I say, okay, I want to give each person 3/5. But look what happens. After you take 3/5 of a loaf out of each of the 6 loaves, you now have 6 pieces that are 3/5 and 6 pieces that are 2/5. So if we want to give the other 4 men bread, I have to give them a 2/5 piece. And then I'll have to take one of the other 2/5 pieces and double and cut it in half. So you can see there's like a purple 2/5 piece and a purple 1/5 piece there. And there's a green 2/5 piece and a green 1/5 piece and a other blue color, sort of purplish 2/5 piece and a purplish 1/5 piece. And finally a brown 2/5 piece. So type into the box, why might some of the men be unsatisfied with this way of dividing the bread? You could type it into the box or Okay, and I see people typing stuff in. I see Beth says it's better to get one big slice than multiple small slices. They may not look equal to the people, right? Maybe, you could tell them, hey, it's the same amount of bread, but they may not agree that it's the same amount of bread. It looks like they got two small pieces, everyone got big ones. They may be dissatisfied. You will be getting pieces of bread from several loaves rather than one chang. Yes, it's like an illusion. So check this out. I really love this. Look at page 8. If instead, this is got to be one of the best moments of the course. If instead we think of 3/5 as 1/2, 1/10, we actually can give everybody not just the same amount of bread, but everybody gets a big piece and a little piece. Everyone gets a 1/2 and a 1/10. And nobody can argue that. Now, they all may be unhappy because they don't want 2 pieces, but no one can argue that someone else got more bread than them because each person has a 1/2 piece and a 1/10 piece. Now, this is speculation. Yeah, that perception matters to children for sure. if you have kids. I know with my kids, they're a little older, they're 10 and 14 now, but we used to go to McDonald's and get, a Happy Meal and get them, the exact same toy, thinking no one's going to fight if literally they have the same toy, that's the same color, but they actually would fight about that also. They would get confused which one was which, and then they'd fight about whose was which. So, I don't know, maybe you have kids that do that also, or maybe your kids are less less stubborn than mine. So I really like this though, the idea that there's an application of it. Again, I don't know that they know that this is like true, but it's like we do a lot of sort of guessing. Okay, here we go. Now, something sort of big is coming right now. So let's go back to multiplying. Multiplying a mixed number by a whole number. So this is a very important, instructive question. 3 1/5 times 11. I'm going to teach you how to do this one. So just like before, 1, 3 1/5. And I'm going to go 2, 4, 8, of course, because I'm trying to get to 11. But I hit a major complication right here. I would so like to write 6 2/5 when I double, but I'm not allowed to because they don't have a 2/5 symbol. And that's where we get in the Rhine Papyrus. It starts before they get into the 85 questions. They have a reference table that's called the recto. I don't know what it means exactly, but what the recto is a unit fraction decomposition for 2 over n for n equals odd. We don't need 2 over n for n is even, because like 2/6 can get reduced to 1/3. But when n is odd, we need to know how do we decompose it. So instead of writing 2/5, I look at my chart. And here they figured out that one of the ways of writing 2/5 is 1/3 plus 1/15. So I come back over here and I don't write 2/5. I write 1/3. So you need your recto, your 2 over n chart. And on the final you'll get a copy of one. And when you do your homework, you need it. So pretty funny. Like by today, it's like to us, it's like a little like funny to see. I mean, to me, it's like, wow, if you could have just said 2/5. But that's how they did it. Now this chart, there's a lot of mystery behind this chart. Like when there were multiple ways to write a fraction, why did they choose 1/3, 1/15 versus some other way? It looks, there's speculation that they tried, when possible, to use just 2 fractions instead of more than 2. But if the 2 fractions required a denominator that was really large, they would sometimes use 3 fractions. They'd rather use 3 fractions with smaller denominators than 2 fractions with a bigger denominator. Another mystery is, how do you get these numbers at all? Is there some process for it? And that's coming up at the end of this lesson, how to actually calculate these.
I'm still curious why they didn't write just 1/5 and 1/5 and then 4 1/5 and then 8 1/5, because then you could see you had 1 and then 3/5 left over. Like, it just seems so much easier.
Absolutely. Absolutely. Why, in math, we have times where like people restrict themselves, like the Greeks using a compass and a straight edge instead of using like other tools, like because they want to like be as like pure as possible. But no, I don't know why they did it. Now let's continue. We double the 6. Good news. 6 becomes 12. Good news. 1/3 becomes 2/3. And since they have a symbol for 2/3, we're allowed to do that. But 1/15 becomes 2/15, and we have to go back to our chart. 2/15, according to the chart, is 1/10 plus 1/30. So I come over here. Okay. Okay, good news now. So 12 doubles becomes 24. They were very aware that double 2/3 was 1 1/3. So that's just a fact, that 2/3 times 2 is 1 1/3. And that's a fact they would have just had. So I'm going to write this. I'm going to put the 1 together with the 24. Well, I'll do it on the next step. No, that might make it even more confusing. So, because then I'll have like numbers next to numbers. So I'm going to write 25 and 1/3. Okay, that we utilize this. Good news. Doubling fractions with even denominators. You don't need a chart for that. Whoops, 1/15. I mean, you just take half the denominator. Now, that means the answer is 25 and 6 and 3, which is 34. And we're just going to put all of our fractions. Sometimes it's really hard, so I'm going to like look. I'm going to see what I have here. Like the biggest fraction is a 1. I'll take these 1/3 first. Hold on a second. Why is there a half thrown in there? My answer is like looking a little bit. The answer on my paper is like a little bit off from what I have here. By the way, the Egyptians would know as one of their identities that 1/3. Hold on, let me find it. 1/3, 1/5, and 1/15. I'm just going to make a note. We're not going to do this because I'm not expecting you, but just side note, they knew that was the same thing as 1/2, 1/10. In other words, 3/5 there's two different ways. We wouldn't know. I'm not expecting you to become somebody who'd be like, oh, 1/3, 1/5, 1/15. I'll just replace that with 1/2, 1/10. You wouldn't think to do that, but if this was your entire math, that would be like one of the facts that would be right at your fingertips. So instead, what I'm going to have you do is just list out all the fractions. Let's just make it 1/3, 1/3, 1/5. Yeah, let me make those in, I'm going to highlight them so that I don't. So there's 2 of these 1/5. And then I have this one, no, I have these 2 1/15ths left. Now I am going to permit you, and you'll be very happy about this. I will permit you to go modern now and to just add these fractions up, just new school, just as like elementary school, and you'll see that your answer will be 35 and 1/5. They would have been very good. Like I mentioned, that they knew 1/3, 1/5, 1/15 was the same thing as 1/2, 1/10. So they would change this maybe into 1/2, 1/10, 1/2, 1/10. You see, there's a 1/3, 1/5, 1/15, and another 1/3. But let me go like this. I'll write it like this: 1/3, 1/5, 1/15, 1/3, 1/5, 1/15. Each of those could be replaced with 1/2, 1/10. And then of course the 2 halves would become 1. And the 2 1/10ths would become 2/10, which would be 1/5. So they would be able to get to the 35 and 1/5 using these like memorized identities. But no, I'm not expecting you to memorize that 1/3, 1/5, 1/15, and 1/2, 1/10 are equivalent to each other. But if you want to put yourself into the Egyptian mind and be like trying to like look for things like that, I encourage you to do that, just because it's kind of fun to try to like be in their heads.
I'm sorry, can you tell me how you got the 1/5 again? You adding the 1/3, the 1/3, the 1/5, 1/5, and the 1/15, 1/15?
Oh yeah, if I just did that, just old school, just got a common denominator. So you can get a common denominator of 15 and say 5 plus 3 plus 1 plus 5 plus 3 plus 1 over 15, which is 5 plus, which is 18. Oh, did something go wrong there?
Because I got 22 over 15. I'm just confused. That's why.
I don't know. I got 18 over 15.
Yeah, me too.
Yeah, but well, the question is, do you have just 1/3, 1/5, 1/15, and another 1/3, 1/5, 1/15? Because with the common denominator, you might have something extra in this. Do you just have 6 things?
Yeah, the 2 1/3s, the 2 1/5s, and the 2 1/15s, right?
Yeah, so each third becomes 5/15. So that's 10. And each of the fifths becomes 3/15. And each of the 1/15 is just 15. So 70, 18 over 15, which for us is the same thing as 1 3/15, which for us is the same thing as 1 1/5. So I totally permit you to use modern math as your last step to simplifying the 34, 1/3, 1/5, 1/15, 1/3, 1/5, 1/15 into 35 and 1/5.
Thank you.
But you know, it is pretty cool that they would know that 1/3, 1/5, 1/15 could be replaced with 1/2 and plus 1/10, and it would be a lot easier to add them that way, because then the 2 halves became 1 and the 2/10 became 1/5. Okay, that was an intense question, but it's kind of fun to do. Let's take a look at what we have next. Okay, so for this next one, I have the whole number on the left. By the way, that question we just did, you know, in your notes, just put a big star next to them. That's a critical question. That's a question that if you're wondering, you know, final exams, you know, like 20 questions total. That question has a high chance of being one of the 20 questions on the final. I really like that question. I think it's one of my favorite questions in the whole course. So a little. Now, if the mixed number is on the right-hand side, one second.
Why did they not understand that 8 times 1 and 1/2 and 1/2 times 8 is the same thing and just always do it one way?
Oh, I would think they understood it, but you know, their algorithm was based. You know, I think it has to do with, in my mind, there is a subtle difference between like thinking of 8 times 6. Like if I have there's 8 eggs in a basket, you know, and I have 6 of the baskets, you know, it's 8 plus 8 plus 8 plus 8 versus 6 eggs in a basket, and I have 8 of those baskets, and it's, you know, so imagine you had an algorithm that was just adding, right? Add over and over. You might think of 6 times 8 and 8 times 6 as sort of different things, like 1 6 plus 6 plus 6 plus 6 plus 6 plus 6, and the other one is 8 plus 8 plus 8 plus 8 plus 8, or whatever. So like there's a subtle difference, but no, I can't say why they, you know, why they would have done that. So now in this question, take a look. I would say 1, 8 here. If I go to 2, I'm already too big. I'm already bigger than 1.5. So I can change. So I go back to the beginning and make a half here. I think I did. Did I do this? No, I didn't do this question. I did a division question. So that's how they might do 8 times 1.5. Okay, 12 is their answer. I did something like this with division, but this is doing it with multiplication because I'm trying. My target is getting the 1.5 there. So I'm going to need some fractions because 2 is already too big. In fact, I wouldn't even write it at all because I'm already beyond 1.5 once I put a 2 there. How are we doing? Halfway through. I know that like this feels like enough for already one day, but some of these questions are pretty short. Now, I want you to know for this question that they would say 112, but they would not jump straight to 1/4. They would do a half and then do a half again, half of that. So let's make a note. Don't skip this. Don't skip this one. They would get to 1/4 via 1/2. It was going to take 2 steps. And you might say, well, they were so good at dividing by 2. surely they could divide by 4 pretty easily, just do it in one step, but you always see them doing this in 2 steps. So 1 1/4 gets us 12 plus 3, which is 15.
They probably bill by the hour.
Now here's one. This is kind of, this one's not so much, it's not hard. So this is 20 times 1 3/4, but they have it listed as 20 times 1 1/2 1/4 the way they would. Why don't you take a minute now to think, how would they, what would the table look like for this one?
Professor, did they have an equal sign?
Well, no, the equal sign didn't come up for like thousands of years, but they would write these out in words, you know, they would say is and things like that,
Okay.
total, things like that. So they wouldn't have these numbered, the numbers were a chart for sure, but then at the end, you know, they would just write the numerical answer. Okay, so take a minute to do this one. And yes, we will take a break at 11. As you can see, we're 12 out of 24, so we're about halfway through the slide deck. I think I want to get to maybe, yeah, at 11 we'll take the break. So we have 15 minutes till the break. Okay, so for this one, we need a half and we need a 4. So it's real convenient. We need all 3 of them.
So Professor, on the test, should we go to 2 is 40, then cross it out to show that it's too big, or can we skip that?
You can skip that.
Okay.
I just showed it for like instructive purposes the first time.
Okay.
So now this actually, to me, this review, so the answer is 35. And this also demonstrates a little bit of the benefit of writing 3/4 as 1/2 1/4. Because imagine they wrote it as 3/4. They had a symbol for it. Then they would, how would they do this question? Like it would be hard because they'd have to think, okay, a half, now how much bigger is 3/4 than 1/2? So by having these unit fractions and they're unique, it enables them to do this algorithm. So I hadn't really thought about that so much before, but it is useful. Imagine they had a symbol for 3/4, what would you do? You know, if they said 20 times 1 3/4, you would have to, you know, go like that. And then you'd have to wonder, okay, I'm at 1 1/2. How much more do I need? Because I don't have 3/4. Whereas over here, I literally see the half. So I can see that what's needed is the 1/4. So their algorithms make having the unit, the fractions that we normally write with a numerator other than 1, to have them as decomposed as unit fractions helps us out in that way. Okay, let's see. Okay, yes, number 13. Here we have something, and this is, oh, well, I'm working towards something, so we're doing good. This one's not going to be a hard one. 6 times 1 2/3. The reason that one's not so bad, you might say, wait, if I go to half, you know, I sort of get stuck a bit. Good news for you. You are permitted, because they would do it, to make 2/3 your first step instead of 1/2. And they were really good at 2/3. Whether, because they were also good at multiplying by 1 1/2. So maybe they thought like 1 1/2 times what equals 6 and said it was 4. However it is, you are permitted to jump straight to 2/3, which of course answers this question instantly. Now this next thing is going to be a little bit like, I shouldn't say comical because I don't want to. These Egyptians are very, sophisticated, but yet you will find this kind of like a curiosity. I think it was Scott who asked, "How are we going to deal with 1/3?" Right? Because you skip from 1/2 to 1/4. This is going to be kind of funny. So here they are at 1/18. Now, if they go 1/2, 1/4, they're going to skip. They're going to skip by the 1/3. Now you might think, hey, why not just jump to 1/3? That would be pretty good. But they never do that. Instead, I see this all the time in these the document, the Rhine Papyrus. They always get to 1/3 via 2/3. And then they do half. They are more comfortable with getting 2/3 of 18 than getting 1/3 of 18. I don't know why. I read a thing that said that they're really good at 1.5 and 12 times 1.5. I don't know, but I would like you to do it this way. To always, now I will let you cheat. I will permit you, because how would I know? I'll permit you to get 1/3 by dividing by 3 and then double it. I'm not going to use any science to figure out which thing you wrote first. But I do want to see this step, as unnecessary as that step might seem.
So Professor, one thing I'm noticing, we write on one column 1 1/3 and 24. It's implied about the 18 because of the 1 row.
Oh, so in this last part, I'm kind of putting the answer by
Right.
collecting, right? My goal was to get 1 1/3.
Yep.
So I add together the two things, here.
Right.
So in fact, let me do this.
I just want to make sure for notational reasons that's okay, because you're just saying 1 1/3. Okay.
Over here.
Yeah, I mean, I understand that you added it. It's basically 1 1/3 is 24. I guess it's implied that it was 18 that got you there to the 24, right? By looking up
18
at
and 6. Well, the 1
But what I'm
corresponded
saying
to
is,
this.
if you read left to right, you have 1 1/3, and then on the right column you have 24.
It's mimicking the table at Desmos, like that's the total.
Yeah.
That's the totals column.
So you look at the top row to understand that if you were like a student in Egypt. Okay.
Well, there wouldn't be the top row is each of these rows basically the 1. So there's sort of an 18 kind of implied, like the name of the chart.
Right.
And this 18 here is telling us that 1 times 18 is 18.
Gotcha.
And this 12 is telling us 2/3 times 18 is 12. And this 6 is telling us 1/3 times 18 is 6. So it's implied that this is like a times tables. So each of these numbers on the right is 18 times something. So we need to get 18 times 1 1/3. So we have to do 18 times 1 together. I'm going to go like this because I think it might help also. 18 times 1 1/3 is equal to 18 times 1 plus 1/3,
right,
which is 18 times 1 plus 18 times 1/3, which is 18 plus. So you're right, the 18 is there because it happens to be 1 1/3. But if it was 2 1/3, we wouldn't have the 18 in there.
Yeah,
If
I mean,
it
I
was
understand
two-
the math. I'm just more concerned the presentation and the notation that you want. That's all.
So this 118 looks a bit like the header,
right?
For the, but I don't think of it that way. I think of it as like N and 18N.
Okay. Thank you.
You're welcome.
So if it was 2 and a
See, we-
third, you would start with 2 in the left-hand column and then half it to 1, right?
If it was 2 and 1/3?
Yeah.
Are you saying?
The first row would be 2 and 36.
Oh no, you still start with 1. You would still start with 1. Are you asking what if the question was 18 times 2 and 1/3?
Yes, sir.
But what are you asking?
The first
Like,
row,
how would you change the question?
the first row would be 2 and 36.
No, the first row would still be 1. So if it was 18 times 2 and 1/3, you always start with 1 and 18. But you would double it to get that. But then you would go down to 2/3 of 18 is 12, and then half of that. And then you would use the 2. So it would be 2 and 1/3. 36 plus 6. So that would be the work if it was 2 and 1/3. Your first row is definitely going to be 118, always. It's just where you go from there. Do you double it? Do you half it? In this case, we doubled it, but then we ended up taking 2/3 of it also. I think of this as going from here to here, 1 to 2 doubles. But then when I started the fractions, I think of that as going back to the first row and taking 2/3 of each side.
I noticed that we're doing
I
a
didn't
lot.
know-
We're doing a lot of doubling and halving, right? So what if it was 18 times 5 and 1/3? I'm not going to
Mhm.
multiply by 5, right? Because I can only double and halve.
You'd keep
So if it was
doubling until
18
5?
I'd go 1, 2, 4. And then now I have enough to get the 5. And now to get the 1/3, I would do 2/3.
1/3. I see. So you're
And then
taking the
1/3.
whole number and the fraction separately using the algorithm.
Yeah. It's almost like 2 different questions, like
Yeah,
one
it's like
for
2 different
getting
questions.
bigger numbers.
That's right.
Yeah. It's like 2 questions. It's like getting 5 and getting 1/3 separately.
Right. That clarifies it. Thank you.
I also have a question. We've been dealing a lot with like even numbers, but let's say like you started with 20, then 10, then 5. If you had to half it again, it would be 2.5.
Yeah, they were very good with that.
Okay.
And we will see that happening. Having an odd number, right? Because having an even number is easy enough. But yes, having an odd number, like 5, you'd make it 2.5. So having an even number is just, half of it. But yes, they are going to pick up some halves, but not much more than that. Because once you start having the fractions, you double the denominators. But you are right. You might have to pick up a half somewhere. Let's look at number at page 15. Now, this is really kind of funny to me. I shouldn't be saying it's funny. Funny is not the word. It's more like curious, and it's like in that world. So look at this question. This is such an unusual question, but for being an archaeologist, archaeologists would never say something's funny. They would say it's intriguing to them. So what's intriguing about this question is that the thing on the right is the same thing as the number 2. 1, 2/3, 1/3. Yet we see this question in the Rhine Papyrus. And that's because this question was kind of like in Plimpton 322, like, just to practice your skills. So 1/12, 2/3, 8, 1/3, 4. And they got 24. You might say, why didn't they just turn the 1 2/3 into 2? Well, the purpose of this question was not so much what's the answer, but are you good at taking 2/3 of a number? Because you might be good at doubling. 12 times 2 is 24. But that doesn't mean that you've mastered your 2/3. So this question comes up. And that's interesting to me that they would do that question as a way of getting good at taking 2/3 and then taking half of 2/3. Okay, I think that is, let me just look at what the next question is just to make sure that that's a good stopping point. Yes, perfect stopping point. 10-minute break starting right now. I'm going to pause the recording. Oh, wait, I'm early. Still got a couple of minutes. Okay, hey everybody. So that was a 10-minute break. I am recording again. As you can see, today's lesson wasn't as there's not as much opportunity to be working in groups on these questions because they're like, unlike the Babylonian ones where there was like a lot of discussion, what decisions to make. This I have to show you all these kind of like little questions. Each one's got its own little trick to it. None of them are long enough to be like worthy of going into groups and having a 10-minute discussion about them. But I hope, and so I hope that you still sort of actively engage in that way. Okay, so what's left? Okay, mixed number by mixed number. So in our modern day, we'd say 2/7 times 7/4 equals 1/2. Totally easy. You would cancel out the sevens. But since they don't have a nice way of saying 2/7 and 7/4, instead, this is a mixed number times a mixed number. So let me take you through. So 1/4, 1/28. That's right off of the that's off of the 2/n chart for 2/7. 7/4 is 1 3/4. So of course that's 1. I'd say 3/4 is pretty much the easiest fraction to turn into unit fractions. And I'm going to take you through this one. On. Okay, so we make our chart with the 1 here and the 1/4 1/28 there. Now, as I mentioned before, it's nice because we could actually see where we're going with it. So we need a half. Now, you have fractions that have even denominators. Sorry, you have fractions by doubling the denominators. So we end up with pretty big denominators. And now to get the fourth that I need, I have to do half of a half.
Where
But
is
to
your
double
half?
the
I'm sorry, Professor. Where's your half on the right column, first row? You have 1/4, a 1/28. Yeah, where's the 1/2?
Do you mean, see this 1/4, 1/28 is over there. And then I always put a
I
1 in that spot. And
Okay,
now
right.
my goal, my target is this. So I can see that I've got the 1, but I need the half here and the fourth here. Now this fourth, you double the denominators. And we were getting quite large denominators, 112. I see questions in Rhine Papyrus with huge denominators with, in the thousands. In fact, you can see in the 2/n chart. Where's that 2/n chart? Here in the 2/n chart, you can see the biggest denominator. They're actually not like so big. I see 606 there, 301, 790. Looks like all the denominators are less than 1,000 in the 2/n chart.
Oh, Professor, so you got 1/4 and 1/28 by looking up 2/7 on the chart, right? The Ronco chart?
Well, this question was going to actually start this way.
Okay.
This is how the question was given.
Okay.
I put the I put the 2/7 times 7/4 just to compare modern versus old. But
Got
on a test, I wouldn't write 2/7 times 7/4.
Oh,
I would give it to you already in this
awesome.
form.
Thank you. Okay.
So our answer is 1, 1/2, 1/4. And we're going to just stick all these fractions next to each other. I like to put them in order from smallest denominator to biggest denominator. And I am going to give you permission to use common denominators, which is actually 112. And it becomes 56 over 112. It's finally 1/2. So I'm just going to make a note. They had their own tricks for combining those fractions. We don't know those tricks or which tricks they would use, which I don't have a comprehensive list of identities that they would use a lot to do these in their head or whatever. So we're going to just go modern and get a common denominator and reduce it and just because otherwise you'd have to just leave the answer like this, which would not be that useful for like practical purposes if the answer is 1/2 at the end. But they were good at combining fractions. They were like little patterns. Sometimes I feel like I'd like to become a master of this and do it, but there's only so many things in life that you can have time to master. So which Egyptian fractions did the Egyptians use as shortcuts? And there are people who study this as their life, so they would know that kind of stuff.
Hey, Professor, you say the Egyptians know this, but is the average Egyptian knowing this, or is this something just like a math class knew, like in Babylonia?
Yes, I believe that the average person would not know this at all, because it's even hard for us with all our modern math and taking all the math that we take now. So no, very few people would probably be able to do this.
But counterpoint, if this was like the way their economy functioned, right, based on trading and stuff, wouldn't the average person actually know some of this?
Yeah, so you know, 1 3/4 to, so I'm not sure of like the sociology of what, of how hard would their calculations actually get like out in the field versus like theoretically what they might be able to answer. So I'm not sure. I have some pretty good books, but I haven't read them all through about like, you know, how they would do these. Okay, let me see how we're doing. 17.
They would probably know like half of bread equals a full beer or something.
Oh, yeah, well, the beer, it depended how good the beer was, because they have like a measure for like the quality of the beer, actually. I'll show you some of those, some of the word problems.
You get the heel for a Bud Light, basically.
Right, the Bud Light. So so let's look at this next question. This one is 1/12, so it's a very small number. And it's multiplying by 2, as you can see, 1 2/3, 1/3. So it's a funny way of saying multiply by 2. But instead of actually changing it to a 2, I just wanted to show you that when you take 2/3 of a fraction, just like when you double a fraction, you take half of the denominator. Sorry, when you take half of a fraction, you double the denominator. So when you take 2/3 of a fraction, you multiply the denominator by 1.5. So just wanted to mention that because it seems like it could be tricky to get to 2/3 of a fraction, but that's your trick for taking 2/3 of a fraction. You multiply the denominator by 1.5. And that's something they were good at. They were good at multiplying by 1.5. They were good at taking 2/3. And then 1/3, of course, is just half of 2/3. And that you can get by doubling the denominator. And now we take all these things together. So 1 2/3, 1/3 is equal to 1/12, 1/18, 1/36, which with common denominators is 3/36 plus 2/36 plus 1/36 is 6/36 equals 1/6. They knew that 1/2 plus 1/3 plus 1/6 equals 1. That was a thing that they were really familiar with, like as far as their facts go. 1/2 plus 1/3, 1/2 plus a third plus a 6 equals a half. Sometimes you could decompose a fraction that's already a unit fraction. So they knew this as a thing they like really would know well. So when they saw 1/12, 1/18, 1/36, they would notice that that's in the same, that's like 2/36. It's like 1/6 times 1/2 plus 1/3 plus 1/6. So I'm just mentioning they wouldn't have to do common denominators because they would recognize this thing as a variation of 1/3, 1/2 plus 1/3 plus 1/6 equals 1 identity. But again, I'm permitting you to use common denominators.
So Professor, 2/3, isn't that equal to 2 times 2? Because 1.
Yeah.
So
that's why it became 1/6 at the end. So 1/12 times 2 is 2/12, which is 1/6. So this is 2. It's a fancy way of writing 2 so that we could practice with the 2/3 and the 1/3 and all. But yes, this is a very long way to do 1/12 times 2. So but they wanted to practice, you know, with multiplying by 1.5, or multiplying a fraction by 2/3 by multiplying the denominator by 1.5. So are you saying that the answer should be a 2 somewhere, or did I answer your question?
No, I'm just wondering, so the Egyptians would break that up, two holes into one into that mixed number like that?
No,
Or
no,
we're
they
just doing
actually
that
had
as
to
an
do-
example?
Yeah, they have this as like practice examples that they do just for the sake of like it's good practice. But no, in reality, they would never start with 1/12 times 2 and turn it into that. But for practice purposes, we're doing that question. You know,
Okay.
1 2/3, 1/3. And we can know that it's right because it gets us the same answer as if we did 1/12 times 2. But no, they would not start with 2 and turn it into 1 plus 2/3 plus 1/3. But it's just for practicing. It's like a drill, you know. It's like in baseball, you know, you might never, you know, do such a movement, you know, or some kind of drill that you're doing, but it prepares you for stuff that might happen, you know, in a real game. Like on a test, for instance, for me, if I said what's 1/12 times 2, I would not be asking you to change the 2 into 1. But if I gave the question this way, I would want to see this work. Okay, how are we doing? 18, 19, 20, 21, 22, 27 questions. Yes, today is one of these. It's a lot of questions. It was 23 questions, but each one is like a little twist from the one before. Unlike in the Babylonian days questions, we just did like 5 or 6 questions. You know, each one was like a big leap. We finish out, sorry, not finish, dividing and applications. So the rest of this class is on division with remainders. So here's 16 divided by 3. Let me just get all my notes. So we say 1 3, double it, 2 6, double everything, 4 12. I'm not going to double. I'll get bigger than 16. So I look at where I am. I'm at 15 now. I need 1 more. Anyone have a speculation about what the next thing is going to be? I just need 1 more thing to add. So someone want to speculate? You could just call it out.
You have it.
1/3.
Yes, they do need to get 1/3. But how would they get there?
Would you put 2/3 and then have it?
Yeah. They just as unnecessary as this step seems, it's like they always do it. So we should do it also. Just maybe that will help us get into their minds a little bit better. They get to 1/3 through 2/3. And the answer to the question is 1 1/3.
Isn't it 5 1/3?
5 1/3. Thank you. 4 1 1/3. I know it seems, and on the final, I would, if this was like an 8-point question or something, I would take off something for not having the 2/3 too. You know, like not a lot. I'd say take off 2 points, take off 1 point. I don't know, but just because it's just a curiosity that I want us to like just be mindful of, even so you always get to 1/3 through 2/3.
Professor, I noticed this. So when we multiply, you always bring the left number over and put it down the column, but with division, you don't, right? You just bring the divisor down. Well, the chart that I'm making is the same chart I'd be making for multiplying, right? I double,
When you say bring down,
Well, if it was
what do you mean?
16, if you said 16 times 3, you would write 6 down the right column, but here you're bringing the divisor on the right down. I'm just noticing, you know, how does,
Oh, yeah. Yes, that's right. That's right. Because 16 divided by 3 is basically saying 3 times what is equal to 16.
right. But I think it's important.
That's what.
That's all.
Yes. So if you're thinking in terms of like when it was multiplying, we took the number that was like on the left, and when it's dividing, we're taking the number that's on the right.
Exactly.
That's true, but it's true because yes, this 3 is on the right, but it's actually on the left of 3 times what equals 16, which is like the equivalent question. But yes, it is worth, if you were like thinking, okay, I take the number on the left, you're correct to say that in division, it's this thing that we make the chart based on the divisor when we're doing division. You're right about that. And I will post the video for this whole lesson afterwards also. Okay, 6 more questions. 22 divided by 12. This is an opportunity for you to talk to your neighbors. So I'm going to put you into groups for this one, because you might, well, so let me there's one answer, but since there's actually 2 potential ways you might write the answer. That's what I want you to talk about with your neighbors. So I'll go like yesterday, the 5 groups, use participants. So I want you to talk about 22 divided by 12 let me give you like 8 minutes to think about that. And I know some people want me to switch them manually into rooms, so I can do that. Oh, yeah. Okay, so are people popping into the rooms? 20, yeah.
Yeah, can you put me in a room, Professor, please?
Yes, please put me in a room.
Okay, so 1 second. That was Scott into room 3. And was it John?
Yes,
Who else wanted to?
John.
Okay, John. I'll put you. Which do you want to be in room? The math. Which room do you want to be in?
Any math teacher room is fine.
Was that is that what 1 and 2 are?
I don't know. I don't know.
I think it's 4. I think it's 4 and 5. Okay, now 1, 2, 3, 4, 5, 6, 7 people. Are you here?
Yes.
Okay, is there, are you having, do you want me to put you into a room, or are you able to?
Yeah, you can put me in a room. Is it math?
Which
Major in math?
yeah, okay, I'll put you into a room. Is there anyone else going to the math major room?
I would go. I would go.
Yes,
to that meeting.
Yes, and some
Okay,
like to.
Okay, so I have you going into room 5. Oops. What happened there?
I solved the question. It's fine. You can. Okay.
Have you guys, are you guys here?
Yeah, we are. Well, at least I am.
Yes.
Oh, you are? Okay, so did you, is, you want to be in a breakout room?
I already solved it, so it's fine for me.
So who's saying that?
Yvette is icy. I cannot change the name. I don't know why. But it's Yvette.
Okay, what room do you want to be moved to?
I already solved it, so it's fine.
Oh, you solved it on your own,
Yeah.
just to see, because I don't, I just want to make sure people aren't like missing in action. So so Crystal, are you here?
Yeah, I'm here.
Okay, and Molly? And Arafat?
Yes, I'm here.
Okay, and Jonathan?
Yeah, yes, I'm here.
And how do I say it? It's spelled Joan, but is it Joe? Is it pronounced differently? How do I say your name? Do I say Joan?
Joanne.
Joanne. Okay, great. So you're here. Okay, so everyone's here except Molly. Okay, I guess you guys could be like a breakout room and talk to each other. The people who aren't in a breakout room.
So for me, I put 1. 1 is 12. And I put 1/2 is 6. I heard the professor says we need to put 2/3 to find 1/3. So I put 2/3 is 8, 1/3 is 4. And I found out that if I use 1/2, 1/2 and 1/3 is gonna be 22.
Yeah, I followed the same thing that we did for the last one, but 16 divided by 3. So
Yeah, I got the same thing, pretty much. Yeah.
Okay, now good news, there's actually only 3 questions left. Because some of these were like the same question twice. So as you can see on this one, well, the answer is 1 and 5/6 by modern, the way we say it. But depending on whether you started by doing 1/2, if you started with 1/2, you would have noticed, okay, I'm at 18, I'm 4 away. I better go to 2/3, might get me, you know, if I keep having the 6, I'm not going to get the 4 that I need so well. So you might have switched over to the 2/3. But if you started with 2/3 and you have the 8, then you'd be 2 away, and 8 divided by 2 is 4, and 4 divided by 2 is 2. So you could have achieved the answer that way also. And this makes me think, you know, they knew that 5/6 could be written these 2 ways. Maybe that's how they figured out some of these ways, with, you know, by doing division problems and just trying the division problem 2 different ways and getting 2 answers that are equivalent but look different. Now, there's only 3 more questions.
Professor, before you go to the next question, the previous question, 16 divided by 3, I feel like you used a different algorithm. Like you had doubling and then you did the 2/3 and half the 2/3. Whereas here you're starting with 1 and you're just halving.
Well, 12 was 12. 12 times 2 was already bigger than 22, but in the other one, 3 times 2 is still less than 16. So we needed both fractions and whole numbers to get all the way up to 16. So if the number is bigger than half, like 12 is more than half of 22, then you won't have the doubling happening at all. But if it is bigger than half, if it's bigger than, so the reason why is that the 12 is bigger than half of 22. So doubling
Okay,
it.
so
is
you
gonna give
couldn't do
you
the doubling because 12 becomes 24 and then it doesn't work. So now you have to start with halving because it's less than 22. I understand now. Okay.
Okay, great.
It's a bit confusing.
Okay, now. Oh yeah, well this stuff is definitely, like, if you compare today's lesson to the other days we had these like big concepts, you know, with like a formula, x minus y squared plus 4xy, you know, things like that, and how can we apply this formula? And this is more like, it's the same trick, it's more like, but in this situation, how do I apply the trick? Now I'm going to show you now. Remember the
I have a
mysterious
question.
2? Yeah.
Right. When you're doing the division, if you're seeing that like 1/2, 2/3 isn't working out, can you skip to a fraction like 1/5, 1/6 to get the numbers that you need?
Well, if you're talking about 1/6, you go 2/3, 1/3, 1/6. You work your way down one step at a time. But I think what you mentioned about 1/5, and do they ever have 1/5? Because sometimes you might need it. So yes, 1/5 is coming, and I'll show you how 1/5. Because I think what you're saying is that, like, yeah, halves and 2/3 are great and all, but what if I need a 5? What if the answer is 1/5? Where's that 1/5 going to come from? It's not going to come from a sum of half, a fourth, and 2/3 and 1/6. So 1/5 is coming in one of these examples that were the last example. So good question. It's coming. Now remember in the 2/n chart. The 2/n chart, we're so many pages back, but the 2/n chart has on it 2/5 is 1/3. Oops. The 2/n chart has 2/5 equals 1/3 plus 1/15. And we actually, you know, we used it in, we used it right here, right? We needed it. So, but the question is, where did that come from? Well, that came from, and the very first part of Rhine Papyrus is the calculation of 2/3, 2/5, 2/7, all the way up to 2/99. Creation of the 2/n chart, which is called the recto, is what it's called. It's just a reference table. Well, we can work those out by doing 2 divided by 5. Now 5 is bigger than 2. So no way we're going to be doubling. Now let's just see. I'm going to try 2 different things because this is really hard because we have one. We have 1. I got myself confused. I want to get things that add up to 2 on the right hand side. And if I go like this, we really run into trouble because like the 5's too big, the 2.5 is too big, the 1 1/4 is like seems useful, but now I need 3/4 more, and how am I going to get it? So this seems to like, it seems to be not working well. Some of them may be really hard, but before we assume that this was the correct first step and that it's just really hard, let's just ponder. What if I start with 2/3 instead? Now, they would know really well that that 2/3 of 10 is 6 2/3. That's it. That's just a thing that they would know really well. So 2/3 of 5 is 3 1/3. That's a thing that they would be able to get directly to. Maybe they just knew 2/3 of 5 is 3 1/3. Maybe they knew 2/3 of 10 and then took half of that. Whatever it is, this is a thing that I want you to just know so that you can, so that you can do it if it ever comes up. Now 3 1/3 is still bigger than 2. So I have to take half of that to get 1/3. And half of 3 1/3 is actually 1 2/3. Again, remember before we doubled 1 2/3 and it became 3 1/3? So you might look and say, oh God, that's my instinct would be 1 1/2, that's half of 3, and then 1/6. But 1/2 and 1/6 adds up to 2/3. So they would definitely not. They would definitely get it to the 1 2/3. So that's also a thing I want you to be like, if you ever have to take half of 3 1/3, it's going to be 1 2/3. If you want, you could do it this way, but then you'd have to know the identity that 1/2 plus 1/6 is equal to 2/3. So 1 2/3 is getting close to my target. My target is the number 2. I just need 1/3 more. And here's where they take a shortcut that, after seeing all this stuff, is going to be pretty surprising to you. They jump directly to 1/15 1/3, which seems like a really big jump. I think that the rationale is that 1 2/3 is basically the same thing as 5/3. So 1/5 of 1 2/3 would be just 1/3. This is a surprising jump. I mean, this is the same culture that wouldn't even go to 1/3. They would have to go through 2/3. But yet they seem to be comfortable jumping from 1/3 is 1 2/3 and saying, okay, I really need 1/3 more. I need another 1/3 to add on to my 2/3 to get the target of 2. And they seem to be comfortable with this. So we'll do that also. And this question's done. The answer is 1/3 1/15, which is exactly the same thing that you get on the 2/n chart. Now, there might be other ways to do 2 divided by 5. But, so I just wanted to show you this as a thing to be like wary of. This is probably making you nervous, like, oh no, what other like
Views right now.
Well, are you with me that one in, sorry, are you with me that 1 2/3 is the same thing as 5/3
Yeah,
by modern?
yes, yep.
So how does 1/3 compare to 5/3? Like what portion of 5/3 is 1/3?
Yes, it's 6/3, it's 2, yes, if we add together.
Oh, together. No, but I'm thinking how to get this here. The insight I would use is that 5/3, I need 1/3 more because I have 1 2/3. So I'm so close to the target of 2, but I need a third more. But what I have here, 1 2/3 is 5/3, just because 1 2/3 is 5/3. So a third is a fifth of 5/3. 5/3 is 5/3. 1/5 of 5/3 would be 1/3.
Yeah.
So if I do 1/5 of each of these, the 1/5 of both of these sides, the right side would become 1/3, but the left side would become 1/15 because it's 1/5 of 1/3.
5/15.
That one might take. What's that?
I'm just trying to see what you did here.
This one's pretty hard to digest because it's the first time they make such a leap. Because you can't get to fifths through thirds and halves.
So
you need.
Sorry, Professor, go ahead.
They needed a 15, so it's very tricky. It would have required, first of all, it would require noticing that I'm close to the answer. 1 2/3 is close to 2, which was the goal. And then we'd have to say we need a 1/3 somewhere. But where's it going to come from? Well, there is at least a 3 in the denominator there. So that's encouraging. There's some thirds, 1 2/3. Well, 1 2/3 is also 5/3. So it's, oh, I see. So this thing is 5/3. So if I take 1/5 of each of these sides, the right-hand side would turn into the 1/3 that I want, but the left side would turn into 1/15 because 1/5 of 1/3 is 1/15. This is a hard question. It's like it's like an art form. You have to it's like telling someone, here, go play a jazz solo. It's hard. You don't want to play a jazz solo that you have to be creative, and you want in math, we want an algorithm. But this question kind of defies an algorithm. It requires at some point looking at what I have, where am I, and where do I want to go, and how could I get there? You just might not have known before that it was even legal to take 1/5 of both sides to get what I needed, because they never did anything like that.
So Professor, I understand that 2/3 and 1/15 is 2/5, but I'm actually confused by what the numbers across for them, the 3 and 1/3 and the 1/3. That's, I guess, what's confusing me. What's the 3 and 1?
Wait.
So I understand 2/3 added to 1/15 is 2/5. I get that. But across from 2/3 is 3 and 1/3, and across from 1/5 is 1/3. What is that equal to? What is the 3 and 1/3 and 1/3 significance?
Well, wait, the 2/3 and 1/15s.
I got that.
Never add those.
It is 2 divided by 5 or 2/5. I get that. But across from 2/3 is 3 and 1/3, and across from 1/15 is 1/3. What is the 3 and 1/3 and 1/3 significance?
Okay, that's a good question. So this thing, in fact, I'm going to just write it up more, write it up again, so that, because we have so much stuff on there. So our goal, let's keep in mind what the goal is. The goal is to produce essentially a times tables where This is n, and this is 5n. And I want to get a bunch of numbers that somehow add up to 2. Now, this is confusing because 2 is already less than 5. When the 2 is a bigger number, like a 12 or something, this was sometimes easier to follow. But the process is still the same. I need some, 5 isn't going to add up to 2, so I need to get some smaller stuff. So using half wasn't working out too well for me. So I did 2/3. 2/3 of 5 is 3 1/3. So at least this number, which is 2/3 times 5, it's smaller. So that's good because 5 was too big. Remember, the target is to get a bunch of things on the right that add up to 2. So 5 was too big. 3 1/3 is also too big. So that's why I cut the 2/3 in half to be 1/3. And the 3 1/3, half of that is 1 2/3. And now I'm encouraged because this 1 2/3 is representing 1/3 times 5.
You know what it is? I think you had the 2/3 and the 3 1/3 circle. Now I get it. Okay, I got it. Thank you.
Now I'm even going to continue more though.
Yeah.
We're so close to the target. The target is 2.
Right.
So I need 1/3. I wish I just had a 1/3 here. And you know how we always wish we could just get there in one shot? But often I say, no, you can't. You have to go through having it and this and that. In this case, they jump to it in one shot by noticing that 1 2/3 is equivalent to 5/3, which means 1/5 of it would be 1/3, and 1/5 of 1/3 is 1/15. And now they're finished.
Yeah.
They achieved the 2 things that add up to 2.
No, I get it.
And
I think the
therefore-
problem was that you had circled the 2/3, 3 1/3. I wasn't getting it, but now I see it clearly. Thank you.
Yeah, sometimes getting a blank screen and rewriting it is much better because this was getting that was getting pretty hairy looking.
Yeah, see, the yellow thing was throwing me off. That I get it.
Now the good news is that when you look at the table of squares, sorry, the 2/n table, they actually show the work for it. So they actually show all these steps, so you can kind of see. Oh, I see. They were allowed to like jump steps. Let's see what I have here. That was the 2/5. Oh, revisit. I always like doing this. Revisiting a question from the beginning. Divide 6 loaves among 10 men. And we know the answer is 3/5, but we also saw before that was 1/2, 1/10. So I want to show you how they would have come up with that. 1, 10. 6 is the target. Half gets me to 5. I'm pretty close to the target. You won't, well, you'll believe it because we saw before they jumped. We so wish we had a 1 here because that would finish us up, right? And they permit us to. They just say 1/10. You might say, oh, if they're allowed to jump to 1/10, why can't they jump to 1/3? I don't know. Why can't they jump to 1/6? I don't know. They always get to 1/6 by doing 2/3, 1/3, 1/6, but they have no problem jumping to 1/10. I think they realize that it's they have no choice. It's not like they have a 2/5 that they can use. So they permit themselves to do this. Kind of sneaky. Good. It's good because it ends the question. It's all done. So you might be thinking now, God, I don't know when I'm allowed to skip steps like that. Well, we'll try not to skip steps unless we find ourselves, in this scenario. If you could get to 1/6, or 1/8, but if you find it's not working, you can do this.
But in this case, they could have done 1/5 of 10 is 2. And then having that is 1/10 is 1.
Yes. And for some, they also don't necessarily show all their work. they, in the thing, they may very well have done that. But then just in the papyrus, they just didn't write this step, but they always write the 2/3. So it's like a mystery, it's like, why can they sort of skip sometimes? I like to think that they went from the 1/2, that they went this way and not from the beginning. I just like to think that they were like, okay, I need 1, but they weren't thinking of 1/10, but maybe they were. So on a test, for instance, I'm not going to penalize you for doing, in fact, I probably wouldn't even ask this, I don't know if I'd ask this question. Okay, I think we are at the final question. Dividing 7 loaves among 10 men. And the reason I put this one up there is because it can be done 2 different ways. Equivalent answers, but 2 different ways. So I'm going to put you into groups for about 8 minutes and then bring you back for the last 7. So where we breakout rooms. So you're going to work on this one. There's 2 different ways to do it. I'm going to put all the people in this who didn't move to a room into group 2. Okay, everyone. So hopefully you had a thought that starting with 1/2, half is easier than 2/3. And if you started with 1/2, this would happen. You'd run into a little bit of a snafu, like wondering, am I allowed to do this? Because I get 1/2 is 5, so that's getting close. Here's what they did. They did not jump straight to 1/5. For whatever reason, they jumped to 1/10.
Why
Doubled it.
the low jam?
What? Why do they have this? What was the question?
The question is why we cannot jump at 1/5.
It's a really good question. It seems totally reasonable to jump to 1/5. You know, let's see what happened over here. You know, they like over here. Notice how they jumped to 1/3, not to whereas so over here, this is really puzzling to me. Like it wouldn't bother me if you jumped to 1/5, but I'm just mentioning that they jumped to 1/10 and then back up to 1/5. It's kind of like they took 1/5. I believe in my mind they took 1/5 of this row to get the 1, but they wanted a 2, so they had to then double it. That's different from this one where they just wanted 1/3. But had they needed 2/3, for example, they might have doubled this thing, you know, double the 1/15 next. So that's a mystery. If you left off this step, that even on a test, I wouldn't mind. But I'm showing you that in the actual in the document, they actually have that step there. Again, if you left that step off, would not be the end of the world. But look, if instead you started with 2/3, you would get 6 2/3, which is pretty close to 7. You need 1/3 more. So you take a half of 2/3, you get to 3 1/3. We've seen this trick before. 3 1/3 is the same thing as 10/3. But before I had 1 2/3 was 5/3. 3 1/3 is the same thing as 10/3. So I take 1/10 of that, and it gets me down to 1/3, which becomes 1/30 and 1/3. And that 1/3 is exactly what I needed. Had they needed 2/3, I believe they would have then gone up from 1/3 to 2/3 by doubling it.
Are
So
you
that's why
allowed
this
to
time
jump to 1/30 like you just did, or do you have to do this progression to get there? I guess that's what a lot of us are getting confused, when you can jump and when you can't jump, because it seems like it's a little random.
Yes, well, I notice that when there are a bunch of thirds involved, so 1 2/3 had thirds involved, and hold on, 3 1/3 had thirds involved. So let's say in general, if we see thirds involved, figure out how many thirds we're dealing with and divide by that number, and that will get us to 1/3. So in this one, 3 1/3 was 10/3, so I multiplied both sides by 1/10.
Gotcha.
In this one, 1 2/3 was 5/3, so I multiplied both sides by 1/5. So I guess what the goal is we need to get a 1/3. In this case, that's what we needed. Maybe we needed 2/3. We'd have to double it afterwards. So let's say as a general rule, if you see thirds involved, figure out how many thirds you're dealing with and divide both sides by that number, and then you will be down to 1/3. So in that way, this question and this question follow the same rule.
Okay.
It's just that in this case, it was 10/3, so I had to divide by 10. And in this case, it was 1 2/3, so I had to divide by 5.
So for testing purposes, if we get to 1/3, you'll let us jump. You won't penalize us.
Right, you have to, yeah, you could jump straight from any number of thirds down to 1/3.
Thank you. Okay.
It is, you know, when we look at the actual, I'll finish out today just by showing you what the actual translation of Rhine Papyrus looks like, just so you can kind of And I'll send you a link to this also. So here's a different screen that has the PDF. So here's the question. Oh, you might wonder, which of the two answers did they use in the Rhine Papyrus? They used the 2/3, 1/30 one, not the 1/2, 1/5 one. Oh, and they don't even show how they do it. They just proof, they multiplied it to show that if you actually multiplied 7 by 2/3, 1/30, it became 10. 7, I mean. At 10 times. So it's funny, they actually didn't show their steps, but they show their answer. So here are the loaves of bread problems. And here are the 52 divided by questions. Let me just look at the 2 divided by 5 one. See that? 1/3 of 5 is 1 2/3. 1/15 of 5 is 1/3. Working out. So they actually give a little explanation, of what their thinking was.
Is this in Google Classroom, this document?
I'm going to put it in there.
Okay.
It's not, but it's a really good, nice that this pretty expensive book is like on Google. It was just freely available PDF.
Yeah, nice.
So, okay, so today maybe took a lot out of everybody because we didn't have a lot of opportunity to think about a slow question, and like it was kind of whirlwind, but it's because I made a lot of little questions. I could have potentially made half as many questions and had us think about it and all, but I wanted to do like a nice slow ladder of easy questions building up to harder and harder questions. I'll see everybody on Monday. I made the homework. I want to make this homework due on Monday along with the homework that was assigned on Wednesday, because we really need to master this to be able to do what we do on Monday, apply this stuff. So you have 3 days to complete the homework assignments. There's no delta math about Egyptian fractions. Now, I unfortunately can't stay after today because I have to take my daughter to the orthodontist. I'm really sorry about that. But I have to leave because I have to get her there.
Real briefly, part 3 of the homework that's due for tonight.
Oh, there is no part 3. There used to be questions there, but they're cut out.
No, they're there. I pulled it up right now. It says complete 2/3, 1/15 to 1. Use common denominator 15.
I see. I deleted them from some document,
Okay.
but not from the correct one. So let me
don't do that.
Oh,
So only
no.
part 2?
Yeah. Part 3, I'm going to delete it from the assignment right now. I don't know
good.
why. Yeah, let me get rid of that. Yeah, there is no part 3. I'm just going to delete that right now. So no part 3. Some reason there we go. Okay, it should be gone from the document in a few seconds. 1, 2. Those questions are actually subtraction questions. I'm going to mention them next class, but I don't want to do too much for it. You're welcome. They're gone now.
So we're only doing 1 and 2 sections?
And 4.
And 4.
Oh, and 5. Oh no, there's no part. Part 5 is also gone. That's a really hard question. So now our homework is much reduced now. You'll see. It's only
1,
5, 6.
1, 2, and 4.
Yes. So it's 5, 11, 14 questions total.
Okay.
Okay, so what does part 4 mean? Compute two 9s and compare to the answer.
2 over 9. Like that thing we just did with 2 divided by 5.
Okay, so 2 divided by 9. Got it.
Yes.
Okay, thank you.
Okay.
Thank
see
you, Professor.
guys
Have a good weekend.
on Monday. Thanks.
Professor,
Again, sorry I have to. Yes.
just one quick thing for homework number 4. It's just